In this lecture, we're going to explore together uninformed search, which are search agents that do not require domain knowledge to search through the search space. So there are different strategies adopted in uninformed search. It could be a breadth-first search, or called BFS, in which we expand in the search space the shallowest node. Depth-first search, or DFS, expands the deepest node. We could do something that's combined, in which we have some depth-first search with some limit. Iterative deepening search allows to do a depth-limited search with an increasing limit. And finally, we could expand the least cost node but in the uniform cost search strategy. Let's start first with BFS search. So in BFS search, as I said, we expand the shallowest node first. Shallowest means that the ones that are at the top. So the idea of, just to keep in mind, the shallowest node means that we need to do some kind of level-wise search in the search space. So we're going to go from level to level, and we wouldn't go to the next level unless the previous level is all done. So to illustrate this concept, let's take an example of this simple tree, which actually is a binary tree. Each node has 2 children, and the nodes go from A to O. So initially, we're going to have an initial state, that's the state of the A. And this state would actually be put in the fringe because it's not the goal test yet. Okay, so is A the goal test? It's not. Then we're going to actually put it in the fringe and explore it. So the next thing is to explore this node. And once we explore this node, they're going to put its children, B and C, in the fringe. So now we have 2 nodes, B and C, in the waiting list. Okay, so the next thing to do is to explore B and then C. But first of all, let's explore B. B is explored now. We're going to, so which means that we are checking its status with respect to the goal test. If it's not, if it is the goal test, we stop. If it's not, we're going to expand it and have the children D and E joining the fringe. But because C was in the fringe first, the next step to do is to really explore C. So C will be explored. It has the children F and G, which will be joining the fringe. The next one to be explored is D, because it was in the fringe first. So D will be explored, its children are H and I. And then the next one, so we have now 3, 5 elements in the fringe, okay, with F and G being actually before the nodes H and I. So we're going to expand next the E. The E has 2 children, J and K. And then we keep going. The next node to expand, so all these guys here are in the fringe. The next one will be the F, and we explore it, and then we explore the H. So we see that at each time we wouldn't go to the next level unless the previous level is done. So we're going to explore the G, and then we're going to go back and go to the fringe, and H was before. So H is a leaf, but it's not the goal test, so it's gonna turn into a failure. So this path actually will lead to a failure. I'm gonna check the next one, I, and so on and so forth. So it's a kind of doing level by level until we reach the goal in the search space. The way to implement the BFS is through this algorithm called breadth-first search. You recognize that this is very similar to the tree search algorithm we have seen before, in which we are going to add things in the fringe and test them, and then also include the nodes in the neighbors, and so on and so forth. So it's very similar, except for these lines in which we are going, it's an implementation detail to do a BFS, so we're going to put that into a specific data structure so as we could really respect this order of visiting the nodes that is going BFS. Okay, so the main differences are this line here that actually creates a queue for the frontier. This one that actually dequeue from the frontier, and this one that actually enqueue in the frontier. So just in case you have never seen queues before, it's a specific data structure that looks like this list here. It's typically an ordered list of similar elements that has that are in order. That's what we call FIFO, which is first in, first out. So we're going to respect the order in which we put the elements in the fringe or in the waiting room to be tested. Okay, so we're going to put from the rear of the queue, and we're going to take from the front of the queue. The actions of taking from the front is called dequeue, and the actions of putting things in the rear of the queue is called enqueue. Okay, so typically we're going to add the nodes to be explored in the fringe. So the fringe would be simply this FIFO list that actually respects the order in which we put the element again. Okay, so initially we're going to dequeue the element from the front, test it, and then If it's a goal test, we're going to declare success. If it's not, we're going to include its neighbors. And we're going to include them from the rear, so as the old ones will be having priority. So it's very similar to the tree search, except that actually we respect the order in which we put the elements in the fringe through this data structure, which is actually a queue. So first of all, is it complete? Yes, it is. If B is finite, which means that the maximum branching factor is finite, we don't have an infinite space to explore. The process or the search strategy is complete because we are going to find the solution if it exists. Second, the time and space complexity can be measured in terms of number of nodes. Remember that? So the time complexity is approximated by the number of nodes that are generated or expanded. So remember, so for example, if we have this kind of binary tree in which we have of depth, let's say 0, 1, 2, 3. So the number of nodes that is being expanded here is 1 for the root node, then 2, then 4, then 8, and so on and so forth. So if the depth is, if d is equal to 3, this means that actually we're going to stop at a solution in the depth 3. So the depth would be, let's suppose that this is the solution, right? So if d is 3, the maximum we could go would be d equal 3. The branching factor here in this case is b, and it's equal to 2. So if we do the math, it's going to be actually 1 plus 2 plus 4 plus 8. So this is going to be the time complexity. A number of nodes that is being expanded is 1 plus b squared plus b cubed plus b to the d, where d is the depth of the solution. So this would be the solution. All right, so we're going to the asymptotics, which means that we're going to estimate what would be the worst case scenario. So this is called the big O. The big O of the time complexity would be the largest term, term in the time complexity here, which would be b to the d. So this would be an estimation of how time consuming is the methodology, so which is unfortunately exponential. Similarly, the space complexity is a big O of b to the d for similar reasons. And if the goal test is applied at expansion rather than generation, then it would be an order of b to the d plus 1, which is pretty close. It's also unfortunately exponential in the space of the number of nodes. So now, is it optimal? So remember, the optimality means that does it always find the least cost solution? Yes, it does. If the cost is equal to 1, we are going to get, to pick up the shallowest solution, which would be, which will have necessarily the least cost solution. So for the implementation detail, we're going to implement that as a fringe, as a first in, first out kind of list. And there is a mistake in my slide. Sorry about that. So it's not a stack. It's rather what we called a queue, right? So it's a queue on which we are going to put elements from the rear and get elements from the front, just to respect the order. This will allow us to go with the BFS approach. So a question actually here is, if time and space are complexities are exponential, why do we even use BFS? And the reason is that it depends on the problem. For some problems, the solution is so shallow that it is much better to do a BFS. You get it sooner, and you won't get really this exponential complexity in time and space. So if the solution is shallow, and you know that from domain knowledge, you could then use a BFS rather than going very deep into the search space, as would DFS or other methods do. Okay, so it could be useful for some applications, but in general, it has exponential time and space complexities. So how bad is BFS? So first of all, let's estimate with some examples with a branching factor, let's say of 10, how much would it be to use BFS in terms of time complexity and space complexity. So it's going to be in terms of seconds or days, in terms of kilobytes or more. Okay, so first of all, let's suppose that we have the following assumptions. So suppose we have a branching factor of 10, and we also have, we process 1 million of nodes per second. This is to estimate the time. And finally, we also use 1,000 bytes to represent each node in the search space. So for this specific configuration, we'll have something like, so we have a root that actually is branching to 10 possible nodes, so that has 10 children, right? Each child has also a maximum of 10 children. So that's the same branching factor. That's also B. So remember, the complexity is B to the D in terms of number of nodes. So we're going to actually calculate for, so this is the level, this is level 0. This would be level 0, level 1, level 2. And remember that, so that would be the D, that's our B, the depth. So that's going to be actually for the first node, we'll have, if we do the total, it's going to be 10 possibilities. For the second level, we will have, so that would be for the first level. For the second level, we will have 10 to the 2, which would be 100. So the total would be actually 100 of 10 nodes generated for depth equal to 2. So I'm going to do the similar process. And you could say that actually the number can go really exponentially. For a depth of 16, we would need to store 10 to the 16 nodes. Given that each node will have 1,000 bytes to represent it, this is going to represent 10 exabytes of memory space requirement. That's huge, and none of today's computers have this capacity in memory. How about the time? Maybe the time is better? No, it's also exponential. So time is also a B to the D. And if we cause that 1 million of nodes are processed per second, we're going to end up with a time of 350 years to process and do a full breadth-first search and reach a depth of 16. This is huge. Nobody has such a machine, and nobody has 350 years to wait until BFS gives an answer, assuming it has to reach the depth of 16. That's actually bad news, which makes actually memory requirement and exponential time complexity as the main and biggest handicap of BFS. But as I said, in some applications, the answer is not in depth 16, it's shallower, which means that we are going to get the answer easier. So if it's at the 6th depth, you're going to just spend 1.1 second and you're going to use 1 gigabyte, which sounds reasonable.